Okay, my 4.1 exponential functions. This is what your homework will look like, or my math lab will look like. Okay, let's grab that first group, which is basically just figuring out what the negative exponent means and how to use your calculator a little bit. So, first one there we've got is 10 to the negative 2. You know that a negative exponent tells you to move down. Move me, move me, move me. So 1 over, move this 10 from the numerator to the denominator. The exponent was a negative 2. It'll now be a positive 2 because you did the work it said to do. And you can clean that up, make it 1 over 100. 1 over 4 to the negative 4. Again, the negative exponent says move me, move me, move me. So this is in the denominator. You want to move it to the numerator. So we're going to get 4 to the 4th power. If you're not sure what 4 to the, it's 256, 4 raised to the 4th power, and you can easily handle that on your calculator. 4 raised to the 4th power gives you 256. And we got 5 to the 0, that one you just got to memorize, 5 to the 0 power. 5 raised up to the 0 power gives you 1. Your calculator will handle it for you if you forget. I know it's easy to think it's 0. It's not. Don't get that confused. 529 to the 1/2. Let me rewrite it again. 529 raised to the 1/2 power. In 0362, you would have learned that this means the same thing as 529, square root of 529. That denominator right there becomes the index right there, the square root of 529. You can handle this one of two ways. You can go 529 raised to the 1/2 power, 1 ABC2 equals 23. Or you can go at it as a square root. Here's the square root key up above the x squared. So second x squared will give you the square root. 529 equals 23. Either one. It'd be cool if you understood that the half, raised to the half, means the same thing as put the radical up there and stick that denominator for the index, which helps you with the next one. We've got negative 1728 raised to the 1/3 power. Again, two ways of doing that. Go straight forward with the calculator, or you can know that any fractional exponent is going to mean you're looking at a radical. Put negative 728 underneath there, and then the denominator is the index. So we're looking for the cube root of negative 1728. So again, either way, let's go this first way. I'm going to put it in parentheses so the negative gets dragged along. Negative 1728, close those out. Raise it up to the 1/3 power, so that'll be 1 ABC3. And there's negative 728 raised to the 1/3 power. That'll give you a negative 12. Check it the other way with the cube root of negative 1728. You want to use this key right here where you've got the choice of what the index is. So I'm going to go second humpy. Oh, I forgot. You first got to put in the 3. The TI requires that you put in the 3 first. So let's clear it out. Tell it you want to do cube root, second humpy. So that 3 is in the x place. It's the cube root of negative 1728. And that'll also give you negative 12. And then we just have a couple of problems where you're just practicing with your calculator. 3 raised to the negative 2.7, just want to be sure you know how to do that. So 3 raised to the, and then negative 2.7, just real clear, you just have to know the humpy key. And that'll give you, we'll put it to 4 places. So 0.05149. Let me see if that's making my screen there. Yeah, barely. So we got 1, 2, 3, 4 numbers. This one tells you to round up, so that one will become a 5. So decimal point 0515. And then the last one in this group is E raised to the 2.5. So let's find our E key. It's up here. It's in the gutter. So natural log. We'll hit that natural log in a couple of sections. But anyway, second to get to the e, and it's e raised to the 2.5. And that'll give you 12.18249. Fourth place is right there. 9 tells you to round up, so we'll make that a 5. So 12.1825 for that one. Okay, now we're going to do a little bit of graphing. Let's see, number 2, f of x equals 6 raised to the x power. This is an exponential function. You can tell because the exponent is the variable. The variable is in the exponent position. That's how you know that. Want to put under the x column, -2, -1, 0, 1, and 2. We'll figure up those 5 numbers and then graph that graph. So this is 6 raised to the -2 power. Remember, it's negatives that negative exponents tell you move him, move him, move him. So we get 1 over 6 squared, which is 1/36. Then we've got 6 to the -1 power. Again, the negative exponent tells you to move him. We get 1/6 there. 6 raised to the 0 power. Anybody raised to the 0 power is a 1. And you know in these exponentials, we're going to have that anchor point, 0, 1, sort of the belly button of this parent function, of any function. 6 to the 1st power is just 6. And then 6 raised to the 2nd power is 36. Okay, let's look at that graph. Getting a little bit low there for you. Let me bring this down. Oh, that's a nice noise. Okay. Bump it up a little bit there. Okay. We've got -2, 1/36. So -2 and then 1/36 would be just barely above that. -1, 1/6, barely above that. 0, it doesn't even look like barely above. Let me move it a little bit higher. Then we've got 0, 1, 1/6, and then 2/36, way, way up there. This is a big number, 6. Remember, 2 to the x power looked like an exponential curve. 3 gets steeper, 4 gets steeper than that. 6 would be about the most steep one we've looked at, I do believe. So here we've got this asymptote here on the y equals 0 line, coming through here, and then screaming up high. So that's what that one's going to look like. You're matching on those in my math lab. So it won't be, you were not, and even if you were drawing them for me, not picky on that. The idea is more important than anything else. Okay, so that's all we need to do on number 2. Let's move to number 3. I think I'll go back up there. Okay, we're graphing f of x equals 1/5 raised to the x power. Remember, that's going to look like the reflection across the y-axis. This guy looked like this one. This guy's going to look like that. So let's figure this up. Let's look at what we've got here. -2, -1, 0, 1, and 2, same as before. Always, always, always. If we've got an x for the exponent, put that series of numbers under the x column. Then we've got 1/5 raised to the -2 power. Move me, move me, move me. So we've got 5 squared. We get 25 for that. Then we've got 5 to the -1 power, 1/5 raised to the -1 power. Again, the negative exponent says move me, move me, move me. So we get negative 1, 5 there. 1/5 raised to the 0 power. Anybody raised to the 0 power is a 1. 1/5 raised to the first power will give us 1/5. And then 1/5 raised to the second power will give us 1/25. So let's go graph those. I think I'll go ahead and turn it sideways. And that'll be good. I'm sorry about that glare. That'll take care of the glare, and I think we've got both there. Okay, good enough. Let's see. -2, +25 is our first point. -2 and +25 is way up there. Bam, way up there, even taller than that, of course. -1, +5 is right here. 0, 1. 1, 1/5. And 2, 1/25. So just this idea right here, screaming up high here, coming in, and coming along that horizontal asymptote. So that's the graph you're looking for. Again, this is a 5 here, so it's a bit steeper than when we looked at 1/2 or 1/3. 1/10, if we were to look at that, would be lying in here and hugging even closer to the x-axis as it goes out toward infinity. So remember, the larger the denominator, the steeper the climb, or in these, the larger the base number itself, the steeper the climb on the right-hand side. Okay, let's look at some transformations. Number 4. Number 4 has got graph f of x equals 3 to the x power. Then we'll graph g of x equals 3 to the x plus 2 power. Okay, let's go ahead and go through the 3 to the x. I mean, if you're comfortable now that it's going to look like that kind of idea going through 0, 1, I'm glad that you're there. If you're not, again, -2, -1, 0, 1, and 2. We'll go ahead and do 3 to the -2. 1/3 squared, which is 1/9. 3 to the -1. Exponent says move me, move me, move me. So we get 1/3. 3 to the 0 power is always a 1. Anything raised to the 0 power is a 1. 3 to the first power and 3 to the second power. So we would graph that. -2, 1/9, -1, 1/3, 0, 1, that belly button, 1, 3, and 2, 9. Horizontal asymptote, it's never going to get onto the x-axis, and then screaming up there. Okay, that's f of x. Let me label that f of x. Now what we need to do is find g of x. G of x is a transformation on that idea. So what we've got for g of x, it is 3 to the x plus 2. So that tells us that what we want to do is transform here. The plus 2 is attached to the x, and you know that's always a liar. So on the x-axis, we're going to shift over 2 to the left. So we want to take this belly button and shift it to the left 2. That's what that's telling us to do. There is no number out here, so we're not going up and down on that, just to the left 2. So we're just shifting this. G of x is to the left 2 units. So the belly button moves to the left 2 units. That may be all you need, and certainly if you're matching on My Math Lab, that's all you're going to need. You're just looking for the second function to be shifted to the left 2. If you're a little bit pickier about that, you're taking this 1/3 guy and moving him over, taking this guy and moving him over 2, taking this guy and moving him over 2, taking this one and moving him over 2. That's the concept. That's what we're doing here. And so then, sort of missed this here. There we go. Something like that. So this is g of x. The basic 3 raised to the x power shifted to the left, 3 to the x plus 2. That's what we're doing for number 4. It goes back to the transformation of graphs. I mean, we've studied them and studied them and studied them. They all behave the same. Once you know the parent, knowing what this tells you is an easy shift. That's what we're going to do on number 5 also. Let's see. Number 5, we're going to get 2 to the x and then 2 to the x minus 4. Very similar problem. You can fast forward through this if you're getting better at this. Number 5. Let's see, we're looking at the parent 2 to the x, and then we're going to transform that 2 to the x minus 4. Almost all in there. -2, -1, 0, 1, and 2 on the x column of your t-table. 2 to the -2. 1 over 2 squared, so 1 over 4. 2 to the -1. Negative exponent says move me, move me, move me, so we get 1/2. 2 to the 0 power, always a 1. 2 to the first power, and 2 to the second power. Okay, let's graph that parent. -2 1/4, -1 1/2, 0 1, 1 2, and 1 4. Something like that. 2 to the third power would be 8, so 1 2 3, and then up 5 6 7 8. Didn't miss by much. So that's the idea. That's f of x. Now we want to transform that one going with 2 to the x minus 4. You know that's a liar right there. So this is going to be a plus 4 to the right. G of x will take this function and scoot it over 4 units. So take the belly button, 1 2 3 4, right there. And if you prefer, if you'd like to, go ahead and move the other points also. Not essential. I mean, you know, you can draw that in pretty decently, but just so you see, everybody's shifting to the 4 to the right. 1 2 3 4. 1 2 3 4. Scoot this guy over. And that guy over. And there's g of x. So you just have to know what that tells you to do. Okay, let's look at one a little bit different. See what happens there. Number 6. F of x equals 9 to the x power, still an exponential function, but using 9, so it's going to be super steep. And then we're going to grab g of x, doing 9 to the negative x. Okay, set this up. X is the exponent, so we want our set of numbers on the x. And that'll drive us to say 9 to the negative 2. 9 to the negative 1, 9 to the 0 is a 1, 9 to the first is 9, and 9 squared is 81. That'll be pretty steep. -2, positive 1/81st, you know, it's on the dot, on the line. -1 1/9, again, hardly above that. 0 1 1 9, and then 281, not going to be able to show that. Don't want to go below that line, doesn't go below it. Oh, it gets so close to it. And then before we hit this second line, 2, it's got to get to 81. So that is just really so steep. And that's f of x. Then what we want to do is we want to get 9 to the negative x. That is a reflection across the y-axis, but I want to show you why or how or whatever. I want to show you why that works that way. So let's look at that. Let's build our same table for g of x. Same numbers. And then what we're going to do is we're going to go 9 to the negative x. So that's going to give us 9, put a negative, and then go grab x, -2, which gives you 9 squared, which of course is 81. So we're going to have a -281 for our first one. Let's look at 9, putting -1 in there for x. 9, then a negative, then the x coordinate, -1, which gives us 9 to the first, which is a 9. 9 to the -0 is just 9 to the 0, which of course is always a 1. 9 to the negative, and then it asks you to pull up x. So that is a 1/9, because that negative is telling you, move me, move me, move me. And then 9 to the negative, because the function itself calls for a negative, then for the x number, and we're going to get 1/81. So that's going to set up the flip of what we were just doing. So we're going to have, don't want to cover those up. There we go. We've got -281, and way up there somewhere, way up high, -1 9, 0 1, 1 1/9, and 2 1/81st. So screaming from way up high there, like that. So it's the reflection across the y-axis. You're not going to have to memorize these, don't worry about that. You're just going to have to find it, and you'll be able to use your notes. It's a multiple choice on MyMathLab matching for those. Okay, now we shift gears and start looking at word problems. Interest, boy, real life there. We're looking at both the accumulated, the formula for compounding and the continuous formula. So we got two different formulas we're looking at here. Let me scoot us down a little bit first. And move us up a little bit second. That's good enough. Okay. Number 7. Find the accumulated value of $30,000 if it's left in an account for 5 years and the interest rate is 5.5%. We want to do this 4 different ways: semi-annually, compounded quarterly, compounded monthly, and compounded continuously. So let's first look at compounded semi-annually. So the compounding formula is the busier one. The principal for this problem is $30,000. The rate here, they tell you, is 5.5%. 5.5% is the equivalent of, remember, you take that decimal point and you move it 2 places to the left. So we're getting 0.55. Decimal point 0.55 over n. Remember, n is the number of times that this is compounded. Semi-annually means twice. And we're going to close out the parenthesis and raise it to n, which was twice, times how many years? And we've got 5 years there. So let's keep working this. Get your calculator. .055 divided by 2 gives us 0.0275. 2 times 5 is 10. I'll take care of that now. 30,000. So 1 plus 0.0275 plus 1 gives us what's in the parentheses. I'm going to raise that to the 10th power. And I'm getting a mess. It's good enough for me to hold that place. I'm not going to write all that down. Same game. You don't want to round that number. You want to just leave it. Leave it in your calculator, because right now you're multiplying it times the principal. And that's what we're getting. So after 5 years of leaving this money in this account, 34953, making it look like money. The 30,000 that we put in now is 39,000. So that's pretty good. Didn't do anything with it, just left it there. Let's look at B. In B, we are compounding quarterly. Same formula. Principal, we know, is $30,000 for all of them. We know the rate, got it from over here, 0.055. The number of times this is being compounded quarterly is 4. How many times is it being compounded? And then for how many years? 5 years. So our accumulated value, let's do this, 0.055 divided by 4 will give us 0.01375. I'm going to add it to the 1 and raise it to the 20th power. And let's see, I can add 1 to that. There we go. And I've got in my parentheses. I'm going to raise that to the 20th. I'm getting 1.3, that stuff. Now multiply it times 30,000. I know there are different ways of doing it. As long as you're getting these answers, this final answer, you're good. So what do we get here? $39,421.99, and that 5, there's what our money looks like in this country. This 5 tells us to round it up, so this is 99 cents. This is going to roll over to the next dollar. So $39,422 is the amount that you get if you compound it quarterly. So instead of $39,300, we're getting $39,400, $80, something like that extra. Okay, let's look at C, which is compounded monthly. Same problem. Monthly tells us it's going to be compounded 12 times. 12 times 5 years. Let's take care of this. 0.055 divided by 12 will give us that number. We're going to add 1 to it. 12 times 5 is 60, so we're going to raise it to the 60th power. Humpy 60. That thing, and then times 30,000. So our accumulated value, $39,471.11. Making a little bit more money. Instead of $39,402, we're making $39,407. A little bit of a difference. And now compounded continuously, we use a different formula. Formula you use for compounded continuously is the PERT one. So our accumulated value is 30,000 times E, we'll worry about that in a minute, raised to the rate, which we already know is 0.055 times 5 years. Lots of ways of doing this. If you've got a better way of doing it, like straight from the front, you go ahead. I'm going to figure out what 0.055 times 5 is first. Times 5 gives me 0.275. So E raised to the 0.275. Let me take care of that. E, go in and grab E. It's the second and then natural log. It's in the gutter there. Raised to the 0.275 gives me that mess, 1.316. Multiply that times our principal, and our accumulated value is 39,495.92. So that's where we make the most amount of money, but it's really not a serious difference. Twice a year is 39.3, then 39.4, 39.47, and then we're still going to get to 39.5. So the whole difference between semi-annual and continuous is not that big a deal. Okay, let me grab another piece of paper, and we will work on the last couple of problems, 8, 9, 10, and 11. Today, the day I'm recording this, is the first day that we're meeting on Blackboard Collaborate Ultra. And I'm so hoping that a ton of you will be there and a ton of you will be comfortable with what we're doing and have good questions so that you can move forward. A little anxious about it. Okay, let's look at number 8. This is still my 4.1 exponential functions. Okay, number 8, you have $15,000 to invest. Which would yield more? Where are you going to get more money? So we have $15,000. Which is better, a 12% compounded annually or 11.9% compounded continuously? So we know that continuous gives us a few more dollars, but what happens when we lower the interest rate? We're not getting as good of an interest rate. How does that balance out? So we're looking at both equations. Let's look at the first one first. Okay, so for this one, we're going to use this function plus r over n raised to the n times t. We've got $15,000 to invest. The rate we know is 12%. And you know that it's decimal point, unseen to you, but understood to be right here. Move it over 2 places to get to the decimal. 12% is like 12 per 100, like 12 cents. So let's make it look like 12 cents. How many times a year is it being compounded? Just once. We're raising that to the number of times it's being compounded times the number of years. 2 years, it says this in this problem. We're putting this money in for 2 years. So let's grab the calculator in a second. Let's see, $15,000. 0.12 over 1 is just 0.12. So 1 plus 0.12 just gives you 1.12. 1 times 2 is 2. Well, that was worthless, wasn't it? Let me back up here. I forgot to move us. Okay, there you go. I hope you fast forwarded through that figure and I'd figured out, but let's go through it briefly. My 4.1, we've got $15,000 to invest and we have two choices, 12% compounded annually or a little bit lesser percent, 11.9, done continuously. So the continuously will give you more money, but you're getting less for the percent. So let's just compare them. Here's the formula that you use for whenever you're compounding anything except continuously. Stick them in there. Let's see, we got 12%. 12%, move it over 2 places and we get 0.12. How many times is it being compounded each year? Just once. 1 times 2 years. We've got the stuff in the bank for 2 years. There's 2. 0.12 over 1 gives you 0.12. Add those together. Now, you're caught up. Let's look at the calculator. You can go straight forward from left to right if you know what you're doing. I'm just going to go ahead and take it a little bit at a time. So 15,000, 1.12, 1.12, let's raise it to the second power. Raise to the second power will give us 1.2544. We're going to multiply that times 15,000. It gives us $18,816. Okay, that is 12% compounded annually. Let's back off of this, but increase this. So it's a little bit of a balance. Let's see which one wins. If we're compounding continuously, that's the PERT formula. The principal is still $15,000. Multiply times E raised to the rate, which is now 11.9%. Slightly smaller rate. Scoot that over 2 places to get the decimal equivalent of it. So 0.119 times, and we're doing it for the same length of time, so 2 years. So 15,000. Let's do this 0.119 times 2. And we're getting E raised to the 0.238. We need to multiply that out. Again, lots of ways of doing this. I'm going to go ahead and tackle E first. Let's get E, and then do the 0.23 E to the 0.238. So we're multiplying times 1.268, etc. Now multiply times 15,000, and we will get $19,030.64 round. So you can see that even though you're getting a lower interest rate on your money, compounded continuously is going to win in this one. Not by a whole lot. It's 2 years later and you're going to make another $200. Not a biggie, but we're not real concerned about making the decision. We're just trying to figure out which is better. Okay, let's move forward to number 9. Number 9 is looking at how much is your house going to be worth a whole bunch of years from now. There are tons of variables in there, tons of variables, but what we're just going to, this is practice using a formula. It's not a real estate class. So let's grab the formula. S equals C times 1 plus the rate raised to the T. It models inflation. So let's see what we're looking at. S is going to be the value of the value some number of years later, the value after inflation. C is the value now of whatever we're talking about. Loaf of bread, a house, whatever. R is again the rate, that's a percent, but we're going to have to change it to a decimal just like before. And then T, just like before, is the number of years, time in years. So let's see what they're asking you for here. This formula models inflation, where C is the value today, R is the annual inflation rate, and S is the inflated value T years from now. So all that information. If the rate is 8%, how much will a house now worth $75,000 be worth in 26 years? So let's see, we got 75,000 for the house value, and we're wondering how much it'll be worth in 26 years. So we don't know what that is. We're going to put in our current value of our house, 75,000, 1 plus the rate. There's the decimal point for 8. Move it over 2 places, and again, it looks like 8 cents. So 0.08 raised to the T, the number of years that we're talking about, looking at what the inflation rate will do to our house. So again, I know there are ways of doing this that will do this in one step. You do whatever you'd like to. So let's see, let's get 1.08 raised to the 26th power. $7.39 and some mess. I'm just going to let that cook in my calculator, because I'm now going to multiply it times 75,000. And there, the value of my house, 554726.49. Okay, so this $75,000 house, 26 years from now, that's a long time. In 2046, that house is going to be worth more than $500,000. You and I both know there's a lot of factors go into that, so I'm not sure that's exactly a good model. So many other things can happen in 26 years. You got to have neighbors that mow their yard for your house to be worth anything too, yeah? All right, let's look at number 10. Number 10 says let's look together at number 16 and 4.1. So what I have done is I've built a crappy little picture here of what that problem looks like, what that graph looks like on number 16 and 4.1. So this is our number 10, but it is number 16 on my math lab in this section. And I grabbed the view and example. So this is the data for the view and example. This graph represents the percent of high school seniors applying to more than 3 colleges. This is the percent along this line, along the y-axis. The x-axis is the year that it happened. So 1980, 29% of high school seniors applied to more than 3 colleges. In the year 2000, 47% of high school seniors applied to more than 3 colleges. In 2013, 67% of high school seniors applied to more than 3 colleges. That's the idea there. Let's see, they give you 2 functions. F of x equals x plus 35. That's a linear formula because there are no exponents involved in it. That draws a line. That's a straightforward line. And they're asking you, I believe in A, they're asking you, yeah, we're looking at the linear model in A. So they want us to use this model in A to determine, let's see, what percent, I don't even know what I just wrote there, but oh well. What percent of these people, of these high school seniors, applied to more than 3 colleges in the year 2010? So they're asking us to look at the data for 2010 with the linear formula, then with the other formula, with the other, with the exponential function, and then compare them. So what you need to know about this is that you don't plug 2010 in there. 2010 represents how many years after 1980. I know we did at least one problem like this in class, So when you've got these formulas, you don't just plop the year in there. They're always going to want you to subtract from some year. So we're asked how, in order to put the number in X, you've got to figure out how many years after 1980 is this number. So it's just 2010 minus 1980, and we'll get 30. That's the number we're going to use for X. It's always going to be based on it's almost always going to be based on the first year you used. So we want to know how many years after 1980 that is. So 30. So to figure f of x, we're going to plug in 30 for x plus 35. So we're grabbing the f function and looking at 30 years after 1980. That'll give us 65% of high school seniors applied to more than 3 colleges. So that's A. B asks you to use the exponential function. G of x equals 32.1 times e raised to the 0.0223x. 0.0223x. So same data. We're looking at 2010. That's 30 years after 1980. 32.1 times e to the 0.0223 times 30 years. So let's grab your calculator for that. I'm going to tackle it the same way I tackled the others. 32.1 times this. Let's see, let's first get this number. Decimal point 0.0223 times 30 equals 0.669. So I'm raising e to the 0.669. Ah. 32.1 times e to the 0.669. So grab e and raise it to the 0.669, and it gives you 1.95 blah 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 times 32.1. So for B, for G of 30, we get 62.7% of students are applying to more than 3 colleges in that year, in the year 2010. Let's see, so what we're asked to do in C is compare the two to the graph. So let's see what we've got here. In 2010, 60% actually. So the actual is that 60% of high school seniors in that year, in 2010, were applying to more than 3 colleges. So what did we get with our linear? We got 65% with our linear. That's 5% off. With our exponential, we got 62.7. That's closer. So the answer would be that B, the exponential function, models it better. So G of x is a better model for the actual facts of this problem. All right, let us look at our last one, number 11. Number 11 is an interesting problem with a heavy message to you, apparently. I like what they're doing here. Scoot us down a little bit. Okay, number 11. F of x equals 70 times e raised to the negative 0.2x plus 30 is our equation, is our function. And it models the percentage of information you can remember after x weeks of learning the information. So x will be the number of weeks after you've learned the information, after you've taken it in and understood it and learned it. So A says substitute 0 for x. 0 for x means that it is no weeks after you've learned it. You learned it right now. So f of 0, 70 times e to the negative 0.2 times 0 plus 30. So we're looking at after 0 weeks. Today is the day you learned this information. No weeks have passed. Let's figure out what percentage of this material you have retained. So we've got 70 times E, negative 0.2 times 0 is just going to give us a 0. E to the 0, anything raised to the 0 power. If you're not 100% confident of that, check it out. E raised to the 0 power is a 1, so this mess is 1. 70 times 1, so that's 70 plus 30, so that's 100%. If you learn the material, after you learn the material, 0 weeks later, same day, you retain 100% of the material. Okay, that's good. And I don't mean exposed to it, but learned it. That's what, learning means you get it, you know it, you're comfortable with it, you understand it. So at 0 weeks, the day we learn it, today we're learning this material, you get 100% of it. B says to substitute 1, so we're looking at F of 1, meaning 1 week after you learned this material. So 70 times E raised to the negative 0.2 times 1 plus 30. So after 1 week's time, E to the negative 0.2 times 1 is negative 0.2. Let's see what we can do with this. Too shiny. E to the negative 0.2 equals that. So we have 70 times 0.818. Don't get rid of it in your calculator. Immediately multiply it times 70. We get 57.3 plus 30. So 87.3% of the material. After 1 week, you recall, or you can retain, what does it say exactly? You can remember 87.3% of this material. Let's see what happens next. Let's look at what happens after, what percent will you remember after 16 weeks? So here they're giving you the X. Here they're telling you the X, and they're asking you to come up with the same thing. What percent will you remember? Same thing. Okay. So we've got F of 16 after 16 weeks. What is 16 weeks? Let's see. Oh, a semester is 16 weeks. So at the end of the semester, something that you learned in January, going to be 70 times E to the negative 0.2 times those 16 weeks plus 30. Let's go ahead and grab, figure out what that is. E negative 0.2 times 16, that's going to give you negative 0.32. Plop that in your calculator just to be sure. Negative 0.2 times 16, negative 3.2. Oh, yeah, one place. Sorry about that. Okay, that's why I checked it. Negative 3.2 plus 30. So now we've got to find E to the negative 3.2. So second E, negative 3.2 gives us 0.0407 blah, blah, blah. Multiply times 70. So we're getting 2.85 plus that 30. So 32.85% of the material after 16 weeks. Not a whole lot of material remembered, only a third of stuff that you knew that you had learned, because you're not reviewing. You can see the moral message that they're giving you in this problem, without a doubt. And let's look at D. D is asking you what percent will you remember after 1 year. So remember, X is in terms of weeks, so we need 52 of those things. 52 of those weeks. The formula, E to the negative 0.2 times 52, get back down plus 30. So at 52 weeks, a year after you learn this material, 70 times E to the
Let's see if I can do a little bit better job there. That's going to be 10.4. Let's see, negative 0.2 times 52, 10.4, cool. Negative 10.4 plus 30, 52 weeks. We need a number in there, so we're going to go e to the negative 10.4, e to the negative 10.4. Oh, decimal point, 4 zeros. Multiply that times 70. It gives us 2 decimals plus 30. Add those together and you get barely more than 30. I was rounding them past to tenths or hundredths. This would have to go to the thousandths to pick up. So basically 30%. So not much more retained. It's just telling you got to review. And of course, these formulas aren't exact. They're models, but blah, blah, blah. Okay, we're good. Go do your 4.1 on my math lab. Get 100 on it. Let me give you a bonus point for that. And I'll see you next time.